So NASA developed a microwave gun that could be used in space where you put the shuttle tile and then you shoot it with this microwave gun and it cure it and stick the shuttle tile. And I wanted to practice on real shuttle tiles, but they wouldn't give it to me because they said, this is proprietary material. We can't share this with you. So Rice has had a long relationship with NASA for many, many years. And my student found a box of shuttle tiles in one of the labs back before they thought this was proprietary. And so we cut them up so that we'd have a lot of them. You know, you're still dealing on pieces. And they came in, they said, where'd you get the shuttle tiles? I said, don't ask, don't tell. But we came up with this technology. And so you see this astronaut with this microwave gun. Now, actually, that's not a microwave gun. That's a water gun that I photoshopped in. But they wouldn't show me the microwave gun. I never saw it. This Nanotechnology Initiative is where it all starts, and we talked about these folks, and Richard Feynman, his 59 lecture, plenty of room at the bottom. He wrote a 1960 manuscript, and then Mikhail Rocco, Richard Smalley, and Neil Lane played a big role. So you actually see a lot of Rice components here because Richard Smalley was at Rice, and Neil Lane was at Rice and then went to be president at another university, then went to the NSF, and then to the White House. So, but he's here now. He's back. He's in the Baker Institute. So here's the important pieces. You had Bill Clinton was a big advocate for nanotechnology, and so the National Nanotechnology Initiative said, okay, we're gonna spend a bunch of money and push nano along. And this was in 1999. So a big deal back then. This was added to by George Bush, and then the Trump administration put more money into it, and then the Biden administration had his focus for clean energy. And then, so if you look at the cumulative amount of money that was spent by the US, it'd be about $40 billion, which sounds like a lot of money, but in light of all the money that's being thrown around in Washington, it doesn't sound that much anymore. But if you look over, now there's not a specific program for nanotechnology. It's more that nano has been put in all the different programs. So the National Institutes of Health had nano, and then they had a separate nano. NSF had a separate nano. Department of Defense had a separate nano. And then they said, okay, no more separate nano because nano is now input into all the key areas. Nano's already there. We're already involved in it. And so they started combining all these things. Nanotechnology is defined by size. You know, there's still some debate. People say, what has nanotechnology ever done? The debate's over. It's incorporated into so many different things. But I will tell you, in many of the products, you will not see it say nanotechnology inside or nano-enhanced. And there's a reason for that. Because like 20 years, more than 20 years ago, there was a big makeup company. They came and they said that they were going to label that they had nano in their product. And then what happened is there was this backlash. Uh-oh, we don't want to put nano on our faces. And you say you have a kid's cream or something, a sunscreen or something, and then you see nanotechnology. People were like, is this going to make my child into a monster or something? So there's nanotechnology is there. It's just people aren't putting it on the bottle. And so there's lots of this. And if you're doing chemistry on molecules, fundamentally that's nanotechnology because you're less than 1 nanometer in size. And the definition is here. It's nanotechnology's understanding and control of matter at dimensions of roughly 1 to 100 nanometers where there's unique phenomena enable novel applications. Now, that means that you have to be sub 100 nanometers, 1 to 100 nanometers in any one of its dimensions. So you could have a carbon nanotube, which we're going to mention in a minute, that might be microns or even centimeters long, but its diameter is 1 nanometer or 2 nanometers. That's a nanomaterial. In any one of its dimensions, it's 1 to 100 nanometers. That would throw it into this area of nanotechnology, but it's trying to control the matter What nanotechnology did, it was really amazing, is it forced people to speak together. It forced people to be able to talk to one another across disparate fields. Because nanotechnology, you'd have chemists working with physicists, same words, remember, same words, same phenomena, but we had different terminology and we had to learn to work together. And so it really combined people together for many years, and now researchers are so used to working across fields, they don't even notice it. But it used to be when you had electrical engineers working with chemists or biologists working with chemists, a lot of times there was a contrast in the ability to work together. And but here we are in these times, and it's encompassed in this nanoscale science and engineering. There's this imaging, there's measuring, there's manipulating this matter at this length scale. So that's what you want to do in nano. And so the matter is called a nanomaterial. So here's the size scale, and you see the size scale where you can be up here at 1 centimeter. You could be around 1 centimeter, and where you might have an ant or something, and then you work your way on down, and you're down to 1 nanometer is here, 10 to the minus 9 meters. And these are the sorts of things that you would see at this scale. Carbon nanotube, again, having about a 1 nanometer diameter, a single-walled carbon nanotube. Then you can get sub 1 nanometer, and it throws it down into this quantum regime. This nanotechnology is more than just downsizing. It is more than just miniaturization. It could be miniaturization, but it's nanomanufacturers is not just about making things smaller and smaller. So like this Indian vehicle, this Tata Nano, a really small car. And this is actually one of our nano cars, which is a single molecule car. We'll have a whole lecture talking about these sort of things. There's a scale up of nanotechnology. How did you take nano and scale it up? How do you start transitioning these things? Because if you just make, say, 1 nano car that's 1 molecule, I mean, nobody can see it. What are you going to do with it? So you have to make lots of these things, and eventually you want to do production with nanotechnology, and it capitalizes on these special materials properties, and promotes integration of nanostructures and functional materials. If you look at carbon, now Rice is really good at nano on carbon. This was really our emphasis. And diamond is like what's in your ring, and diamond is used in many industrial applications as well. So for example, many drill bits will have diamond tips to help drill through material. And diamond is this tetrahedral carbon atoms, and they have this configuration. And then there was this discovery of C60, Buckminster fullerene, and that was discovered in the Space Science Building, just here on campus, by Rick Smalley, by Bob Curl, and by Harold Kroto. Harold Kroto was here for a week. He came to use some of the equipment that Rick Smalley had, and it was during that week, and Jim Heath and Sean O'Brien were the 2 graduate students on the project, and they saw this peak at I don't know, was it 720 or something? Is the molecular weight of C60, and they saw this peak, and they couldn't figure out, why is this peak there? Why is it so stable? And Harold Kroto, who was visiting from the UK, suspected that it was some ring compound, and they went away. It's a really interesting story. When Rick Smalley was alive, I used to have him come in my class and tell the story. And then he passed away, and I used to have Bob Curl come in and tell the story. And Harold Kroto lived in the UK. He's passed away as well. And now Bob Curl passed away last year. So he, I'm the only one left who heard their stories that I can relate to you. But it was really interesting, something that just happened. So I think they started their experiments like on a Tuesday, and then by Thursday they saw this peak at 720, and then Jim Heath, who's now a professor on the West Coast, and Jim Heath and I are around the same age, so it gives you an idea of where Jim Heath was at the time. He was just a graduate student at the time. He had a little device that he had built for this machine, and he got a much better signal. They were trying to figure out what this was, And over the weekend, they figured it out. So it started like on a Tuesday. Over the weekend, they figured it out. They wrote the paper on a Monday. And it was a short paper. Nature used to have like 2-page communication. They wrote one of these 2-page communications, put in the data, sent it out on like a Tuesday. They faxed it in. There was no email sending in those days. And they faxed it in. It was accepted the next day. That never happens. That never happens. They would never accept a paper. They've even said it without going for external review, but they realized how important it could be. So within 1 week, they did the research, they wrote the paper, they submitted it, and it was accepted. It was crazy. And, but that was C60, Buckminster fullerene. And then Rick Smalley had hypothesized. So remember, all you had graphite, which is a chunk of graphite, which is a chunk of a number of layers, and you had diamond. But now there was this new allotrope, this C60 structure. And many people didn't believe Rick. When you come out with a great advance, people don't automatically believe you. They're like, we don't believe this. He just stuck to his guns. And he said, no, it is this structure. And you couldn't get a crystal structure on this because the molecule spins so quickly, you can't get a crystal structure on it. And it's not until somebody, there's a guy named Hawker, maybe? He was at Berkeley. He was an assistant professor. He functionalized C60. He reacted with osmium tetroxide. If you remember back to your organic, osmium tetroxide will add across a double bond. And that put like a big thing hanging off it, and that stopped the rotation. And they got the crystal structure based on the osmium complex, and boom, you could see it. And if you run the NMR, you get one peak. The C13 NMR gives you one peak because all the carbons in C60 are the same. They're all the same environment. So you have 60 carbons, but you get a single signal in the C13 NMR. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. And then he had hypothesized that you should be able to grow nanotubes, these long, that you begin to get a C60 and it would elongate out. And then the single wall nanotubes were found a few years later. So I think this discovery was in like 1985, the C60 discovery, and I think it was in 1996 or 97 that they won the Nobel Prize for this. I think 96, they won the Nobel Prize. And then there's graphite, which is these individual layers like chicken wire, and they're stacked up. If you have more than 10 layers, that's graphite, all right? That's what's in your pencil. When you can make individual layers, then it's called graphene. This was actually found many years ago, and we'll talk about this. It was first discovered in 1964, but there's some guys in I think it was 2006 that re-isolated it, and we're going to talk about graphene. But you see here's this is just printed on a 3D printer, and it's a chicken wire like, right? And so this is graphene, and okay, so there's this, and you can put another layer directly over it. That would be called what's an AA stack. So it's directly over this. But if you slide this over half a unit, and so you can see the difference now. You go from here to here. Can you see that difference? And you get that. And this is the natural ordering. It's called an AB stack. This is what you get in graphite. And then you can have the AA arrangement, or you can just have something disordered. And you get all these nice patterns as it goes through. And when it's disordered, it's called turbostratic. Or you can go to like a 2-degree twist, and this turns into a superconductor. And so it has all of these interesting properties. So we'll end with that, and we'll go right into carbon nanotubes. This is just an overview, and we'll look at the history of carbon nanotubes. Carbon nanotubes, the single-wall carbon nanotubes. So here's the history of it. You had the carbon nanotubes were first reported in 1952 by these two Russian researchers, and they published a clear transmission electron microscope image of 50 nanometer diameter. So these were multi-walled tubes. MWNT is multi-walled nanotube. they were likely people had produced them before, but this was the first time a TEM image. But look where they published it, in the Soviet Journal of Physical Chemistry. I ask you, has anyone here ever read any article in the Soviet Journal of Physical Chemistry? I didn't think so. Neither have I. Nobody read that journal. And so nobody knew about it. Nobody knew it existed. And then in 1976, Oberlin, Endo, and Koyama published what they called a hollow carbon fiber with nanometer scale diameter. And they showed a nanotube with a single wall, like a single wall of graphene. And that's how it was described, a single wall of graphene. So that was in 1976. And many people then thought, okay, well, Endo and his group there had discovered this. But it turns out, if you really search the literature, you find it back in 1952. And then in 1985, buckyball, or C60, was discovered here at Rice by Kroto, Smalley, and Curl. And then in 1990, Smalley postulates that there should be an elongated version. So in other words, you have like the cap of a C60, but then it just grows on out. And he postulated that. In 1991, Dresselhaus made a theoretical prediction about carbon nanotubes. It's saying there should be single wall. And then in 1991, Ajima rediscovered multi-wall nanotubes, where, and again, nobody knew about it. I say rediscovered because in 1952, nobody knew about it. 1976, no one paid attention. And Ajima rediscovered the multi-wall nanotubes. And then in 1993, Bethune and Ajima separately discovered single-wall nanotubes. And we'll see the difference between multi-wall and single-wall in just a second. That was very big news. The person who took the images for Ajima was a postdoc working in Ajima's group at NEC in Japan, NEC Corporation in Japan. And that was Professor Ajayan, who's in the materials department here. He was a postdoc at the time, and he was the one who took the first images of the single-wall nanotube. And Bethune was at IBM here in the US, and they both discovered these, they both rediscovered single-wall nanotubes, but Endo really described a single-wall nanotube. And then Smalley, in 1995, he achieved a synthesis of single-wall nanotubes by laser ablation, where he took a carbon target and he hit it with a laser, and he saw some single-wall nanotubes growing, and he started selling single-wall nanotubes. Cheaply, very cheap. He wanted them out because he wanted lots of people to work on them. You make it available, you make things available very cheaply. I want you to remember this. You make things available very cheaply, and the field really starts to grow. If you say, I don't want anyone else working on it, I want to work on this all myself, then what happens is nobody can work on it and the field doesn't really grow. It's sort of like the internet. When something gets out there, you put code out there and your code gets much, much better because the whole community of coders starts working on it. So you want your invention to get out there. Yeah, go ahead, file your patent. I don't know, maybe some of you came up with inventions this week and you want to file a patent on it. And very soon we'll talk about how you can protect your technology. We'll have a session on how to start a company, how to protect technology, and then do a startup company from there. Maybe you came up with such a great invention, you want to protect that with a patent. So you can do, but then once you've protected, once you've written your patent, you want it to get out there. Get it out there, and so other people can start refining it and using it. So then there was this production of single-wall nanotubes and multi-wall nanotubes. There was carbon arc method, laser vaporization method, lots of methods. But we have got the cheapest method for making nanotubes, and we're going to go over that when we start talking about the flash Joule heating, and we'll talk about a company that we've started that's around that by a former undergraduate. The former undergraduate worked in my lab, and I'll tell you how dedicated of an undergraduate was. You know how as a freshman you move in on Sunday? Monday morning at 6 a.m., he was outside my building, and the janitor came to my office. He said, there's a student out there who wants to see you. I said, okay, send him up. And it was John. John got here on a Sunday, Monday morning at 6 a.m., he's at my office. And he said he wants to start working in my lab. I said, I'm busy now, come back tomorrow. And I just wanted to see, what kind of mettle he had. Was he really dedicated? Tuesday, 6 a.m., he's back at my office. And I said, this kid's dedicated. And so he got to work in the lab. He could have graduated in 2 years. He graduated in 3. I tried to get him a PhD concurrent with his bachelor's degree. But Rice wouldn't let me for some dumb reason. some protocols. But he did more than enough. He's published 20 papers from my group as an undergraduate. The guy had no life. He didn't do anything that undergrads do, except he was always in my lab working. He worked like a graduate student in my lab. So this is the difference between a multi-wall and a single wall. A multi-wall has these concentric rings. That's a multi-wall carbon nanotube, and that's what he's selling. It's much harder to cleanly make single-wall carbon nanotubes. And for certain applications, you want single-wall, but for many applications, which is strengthening composites, high conductivity, all you need is multi-walls, which are much easier to make. Multi-walls are sort of like these Russian dolls, where you have these nested structures, one within another, and lots of ways to grow these now. And people are making AFM tips out of this, and they have this form of carbon. It's a few nanometers in diameter. They can be microns long. Think of this: something that can be a few nanometers in diameter and microns long. In fact, people have grown single-wall carbon nanotubes, which are about 1 nanometer, 1.2 nanometers in diameter, centimeters long. I think the record is now like 20 centimeters long. Think of this. This is one molecule. It's one molecule, 20 centimeters long. So it's like this long, but it's 1.2 nanometers in diameter. So you can't see it with your eye. It's too small to see. It's too thin to see. But remember, human hair is 50,000 times that diameter. Now, there are single molecules in biology. Your DNA is about 2 meters long. Human DNA is about 2 meters long. You say, how does something 2 meters fit into a little cell? It's wrapped up around a histone. It's amazing. It's just amazing that you can wrap this thing up and it packs into the nucleus of a cell. And then it doesn't get tangled up, because it has to unwind, and pieces of it have to come out for duplication to occur. And enzymes take care of all of this. It's really amazing. So they're good conductors, and they conduct heat, they conduct electricity. Single walls, so multi-walls are always metallic conductors. They act like metals. They're always good conductors. Single walls can be semi-metallic, or they can be semiconducting. And semiconducting, now you can have a band gap. So people have thought of a lot of different sorts of devices that you could make out of these things. Now I want you to think of this. This I can't bend too much, it's going to break, but I want you to imagine a sheet of paper. Now I could take this sheet of paper and I can roll it up like this, right? So that the ends are perfectly aligned, right? Roll it up, and I have a tube. Now, I can take this sheet of paper and I can roll it with a little bit of a twist so the two ends are no longer aligned, right? And that twist can be a big twist, a little bit of a twist, or no twist at all. That twist in how you roll it defines how that single-wall nanotube is going to respond, in the sense that is it going to be semiconducting, semi-metallic, or metallic. So semi-metallic is just a poor conductor. It's just a poor conductor. A semiconductor is not a poor conductor. Semiconductor has a band gap and it has very different thermal behavior. A semi-metallic just means, and there's two indices, N and M. And when N minus M is a multiple of 3, that has a milli-eV band gap. That's a semi-metallic metallic. N minus M equals 0. And sometimes these are called armchair nanotubes. The way they get this name armchair, so imagine if this is like a chair on its side. Say we turn this 90 degrees, so a person could sit here and these are the arms for the chair. And then this is called the zigzag edge. And all of that depends on how you roll the thing up. And semiconducting, N minus M is not a multiple of 3. This is how you can define it. So there's these two parameters that assign this. And you get this armchair edge, or you get a zigzag edge, or you get some intermediate, and all of these have different properties. These have tremendous mechanical properties. So you can take one of these, how you can take a straw and you can begin to bend a straw, plastic straw, but at some point, boom, the thing buckles. At that point of buckling, and then you straighten out the straw is never quite the same. It's okay in a nanotube. That thing will eventually buckle. Look at that buckle right there. But then you stretch it up, the carbon atoms just go back to where they were. Now, you can break carbon nanotubes. You can put them in grinders and just mechanically bend them enough that you'll snap the thing. And carbon nanotubes are probably the strongest polymer that will ever be made. They're the strongest polymer that will ever be made. And so how can you make a claim of something that will ever happen? I mean, you can't predict the future. You don't know that. You just don't know that. Well, yeah, you can. This is going to be the strongest polymer ever made. And the reason for that is we have a periodic table. The periodic table is the same throughout the universe. One of the strongest bonds in the periodic table is the carbon-carbon bond. It's about 95 kilocalories per mole, something like that. Something like 400 kilojoules per mole. It's a strong bond. And because these are shared benzene rings, it's not a bond order of 1, it's a bond order of 1.3. So it's like taking a carbon bond and multiplying its bond strength times 1.3, every bond in there. Now, if you have a ladder polymer, 2 bonds holding the structure together. Your typical polymer like polyethylene, you break 1 bond, the polymer breaks. A ladder polymer, you got to break 1 and 2 to break that polymer apart. People go, whoa, ladder polymer, that's a strong polymer. Well, if you have a 10-10 carbon nanotube, you've got to break 20 carbon-carbon bonds to pull that apart. 20. And remember, that's 20 where now that's multiplied times 1.3 each one of those bonds. That's what I'm saying. So we take one of the strongest bonds known in the universe, the carbon-carbon bond, and you have 20 of them that you have to break, each one being a bond order of 1.3. So it's very unlikely you're ever going to get a polymer, a one-dimensional structure, like a line, polymer that's as strong as a carbon nanotube. These things have been modeled. This was a model done by Boris Jakobson here in the early days of looking at these things, where you can pull carbon nanotube, and whatever is red is really under stress. What's blue is not under stress. And you start pulling this thing, and everything is turning red, but eventually bonds are going to start to break, and then they'll turn blue again. You get down to a string of just single carbon atoms, which are not happy. Carbon atoms they want to have more bonds to them. They want to have 4 bonds going to them. They're unhappy, but it's all they got because you're pulling it. So anybody can take a carbon nanotube. If you had 1 carbon nanotube and you could break it. You said, I thought you said this was like the strongest polymer known. It is, but you're huge. This thing is like 1 nanometer in diameter. Nothing else can be that strong at that level. So people will say graphene. Graphene is like super strong, and this is like stronger than steel. It is. It's stronger than steel at the 1 atom thickness material. So in other words, if you had steel, which is a bunch of iron atoms held together just in a sheet, 1 layer thick of iron atoms, that wouldn't even stay together. But when you have carbon atoms, it stays together. You say, well, that sheet of graphene is super strong then. But if you just don't treat it really gingerly, it falls apart. Why? Because you're so big. When they say it's the strongest material known, it's the strongest material known at that level. Nothing else at that level would be that strong. That's what they're talking about. And I still, to this day, get people calling me up, oh, we have this idea. I don't want to tell you. Will you sign a non-disclosure? I'm not going to sign a non-disclosure agreement. What's your idea? If you want help, just tell me. Well, we want to coat the inside of these pipes with graphene. Graphene's so strong, and there'll be no corrosion. I said, look, if you just touch the thing, it's going to come off. It's like a pencil. I mean, it slides right off. It's going to fall apart. They said, I thought it was like stronger than steel. I said, it is. At that level, if you had a 1 atom thick layer of steel, it wouldn't even stay together. So that's the qualifying thing there. Here's an important question. Why would anyone believe that a man named Jesus died and rose from the dead? If you don't believe in the physical resurrection of Jesus Christ, send an email to tour@drjamestour.org and we'll set up a meeting, and I will tell you about why I embrace the resurrection of Jesus Christ. People have wrapped these things, and you can view these by AFM, these wrapped nanotubes by AFM, And there's these vector numbers. Remember I told you these N and these M numbers and how these wrap up. And a lot of research, this was done by Bruce Weissman here at Rice. And he came up with an instrument that's a 3D fluorescence maps. And so when you have a big peak, so here's what it looks like if you look at it in 2D. But each one of these is like a mountaintop. And so when you look at it in 3D, you see these mountaintops coming up, and each one of these is a type of carbon nanotube. The good thing is when you make single-wall nanotubes, you get all the different types. You get semi-metallic, metallic, and semiconducting nanotubes. The bad thing about single-wall carbon nanotubes is that when you make them, you get them all, because you might want just semiconducting, but they all come as mixtures. And separating them, people have figured out ways to separate them, but they're not easy to separate. Because people might say, okay, this has exactly the band gap that I need to build this amazing computer. All right, well, fish the thing out. You're going to get a bunch of metallic ones in there shorting out your computer too. And so you got to fish it out. And the procedures for fishing them out are not that easy. And so people were envisioning this, Rick Small used to talk about a carbon nanotube fiber right up into space. And so you'd put your solar panels up in space, so there's no atmosphere to worry about, and you'd have this fiber that could you could bring the electricity back down to Earth because it would be highly conductive to make these nanotube fibers. So he had a big project in making carbon nanotube fibers, and that's now been inherited by Matteo Pasquale, which, I mean, he helped to originate it, and it's carried it on, and now he's got this company that's something like Daxmat or something that sells carbon nanotube fibers, bunches of carbon nanotubes into a fiber that you can see. And the thing was to make it all out of metallic carbon nanotubes and rewire the grid, very low resistance. With metal wires, you get sagging over time. The metal sags over time. You use aluminum wires, and those sag over time, so you put a steel cable in the middle of it to try to stop, and these wouldn't sag over time and things like that, but you just couldn't make them for the price for the rewiring the grid. And I always wondered about that. What if like an airplane flies by? Is it going to chop off the wing, or is it just going to break the wire? I mean, so this wasn't really well thought out, and they talked about putting solar panels on the moon and hooking the fiber up to the moon, having fibers to the moon and sending electricity back. And if you don't keep the charge right, you'll pull the moon to the earth or something could go wrong. This is carpets. You can grow nanotube carpets. And so you can take a surface, and the way nanotubes are grown is you take a little metal particle, like an iron particle, very small particle, 1 nanometer particle, and it'll start to grow on that, and then it'll start to grow out. And if you drop these particles on a surface, you can get this growth like this, where they're growing up off a surface. And doesn't this kind of look really neat? This is nanotube carpets growing up off the surface. See, that's a thick carpet. Doesn't that look like thick plush? It's only about 5% coverage. It's just like our hair. If you take a person with really thick hair, you say, wow, it's just like every nanometer on their head has hair coming out of it. That's not the case. If you shave their head and you just really zoom in on it and you count it, and we did this with one of our students, and he had a really thick head of hair, and we counted the number of hairs coming out in a square centimeter. And you only have about 5% of your scalp covered in hair. And the rest is just, coming down. This is only about 2 or 3% coverage. It looks really thick, but it just appears that way. And so it's coming up, and you can look at this. And so then we learned a way to grow these, extended this form, and we could pattern these on surfaces, and we made these supercapacitors out of these things. It was really so interesting. And then we made these micro supercapacitors out of them, and we grew these on surfaces. And my student came back, he told me, he said, this is, his name is Yu Zhu. He said, this has a surface area of nearly 3,000 meters squared per gram. So think about that. 1 gram of material has a surface area of 3,000 meters squared. When I heard that it had that large of an area, I said, this is going to make a great electrode, because in a very small domain, you can have a great area of coverage. And then so we use this to make batteries. And that was the birth of this company called Zeta, because somebody brought to me something that had a very high surface area. in a very small area, a very small square area, but because it had these vertical things coming up, had a very high surface area. We knew that it would have great connectivity to this thing because it was like being hooked up to 3,000 square meters. And so you can see how in this company they're growing, here's metal and they have these nanotube carpets. Here's another layer of, this is another layer of metal and another nanotube carpet. So from a layer of metal, you can have carpets growing out of both sides. This is the anode of their batteries. So this is a battery company in northwest Houston, and they've raised something like $50 million to date. And they have a prototype line now for making batteries. But this is the anode, and then they had to make a cathode for it. And so this I just clipped this off their website today. By performance, cost, safety, energy density is high. You can charge it very quickly. You can run it for 2,000 cycles, full discharge, charge, discharge. 2,000 is a lot. Typically with a battery, like for a cell phone, what you shoot for is you shoot for about 700 cycles, because that is charging it once a day for 2 years. 2 years you get rid of the battery anyway, and so that's about what people shoot for in a cell phone. A car battery you won't charge that many times, but the way it's done in industry, you do full charge and you do full discharge. Full charge, full discharge. So when you say 700, that's 700 deep discharges, because the more you bring your battery down, the worse it is for the battery. And it doesn't let you bring the battery down all the way, because that's really bad for the battery. You say, well, it shows nothing, it shows zero. That zero is not really zero. That's the BMS, the battery management system, is telling you it's zero, but it's really like, it's really 5%. It's not gonna let you get down there because it doesn't want you to destroy your battery. Industry, it's a full discharge, full charge. So they really push this. But what's interesting about Zeta's batteries, there's less than 5% after 1 year loss. So you leave your battery for a year, I mean, it's fully discharged. Not Zeta's. Zeta's will only lose about 5% per year, which is like what you would get out of an alkaline battery. That kind of behavior. And then they had to build a cathode for it. We had only made the anode and we sent it out for publication, and the reviewers said, no, we want to see a cathode too. So we built the cathode, and all of this was like in 2013 or something that we were doing this. And now there's a company around it. It just got so good that they were able to start a company around it. This was the system. This was in the third floor of Space Science Building. It is no more there, but this was the system that Rick Smalley built for making carbon nanotubes in his lab. And then this translated to another system, and so you get this hot zone. It was like 900 degrees centigrade in this hot zone. This iron pentacarbonyl would come flying in, and carbon monoxide as a carbon source, and they would mix in what was called the shower head, and poof, the nanotubes would go flowing down these tubes, cooling, and then he'd extract the heat from them to reheat carbon monoxide coming in. And so this is what it looks like under the microscope, but each one of these is like a fiber made up of many carbon nanotubes. So this is kind of an end-on view. We put these in composites. So many things have been done. I'm just giving you an idea. You put these in composites. You can put little functional groups on the side, do chemistry, because if you don't put functional groups, sometimes you put it into composites and it just kind of slides out. But then when you put little jags on the side of it, these little arrow rings on the side, now it interfaces with your composite. Here's two things you have to do if you ever want to have a good nanocomposite. Two really important things. You got to have good dispersion and good interfacial interaction. Good dispersion, in other words, you have to take your nanomaterial and you have to be able to disperse it in the host material really well. When nano first came out, people would take this nano stuff and throw it in, and it was never dispersed well. Then you also have to have good interfacial interaction. So the nanometer material might go in as a powder, but it needs to be exfoliated, separated from one another, so you really have nanometer-sized entities blending into your composite. Number two, you have to have a good interfacial interaction between the nanomaterial and your composite and your host material, or else the thing just slides out. that's why like an arrow has an arrowhead that when it sticks in, you can't get it out because of this arrowhead. Same sort of thing. And so doing that, you can get good composites. So this is a project we had with a company called Hydril, but we could take this rubber, which is in blowout preventers. If you ever heard of the Deepwater Horizon that had a failure in the Gulf of Mexico, that was a blowout preventer that blew out. And that's the thing that closes down. So in a blowout preventer, so you usually have a pipe going through here, and the way it closes is this will crunch down, and when it crunches down, this rubber thing closes off. That's your valve, and then you can open up, thread a pipe down for your oil well. And so if we put it in this rubber, the rubber originally had this stress-strain curve. When we put in the nanotubes, we got this stress-strain curve. And what's interesting about this is, first of all, the area under the curve is proportional to the toughness, the amount of energy needed to break the polymer. And so this is like 3 times the toughness. But not only that, look at the strain at break is almost the same. So think about this. You take a rubber band and you stretch it, it can stretch really far. But now if you put more cross links into that rubber band, what will happen is you pull it, it's much stiffer, but it's going to break earlier. You're not going to be able to stretch it to 3 times its length. It's going to break. This is different. With these nanotubes in there, these functionalized nanotubes, it was much stiffer, but it could stretch just as far before it would break. So to increase the stiffness with no change in the strain to break was a big deal. So this went into those products. And so you can see the effects here. So your typical styrene butadiene rubber could heat to 250 degrees Fahrenheit. In the oil industry, they still talk Fahrenheit, interestingly enough. So if you're a chemical engineer, you're going to have to do conversion a lot of times to Fahrenheit if you work in the oil industry. So 250 degrees, this is a hydrogenated nitrile butadiene rubber, 250 degrees. But we could go 100 degrees higher by adding the nanomaterial to it. I called in a student. This is an amazing story, just amazing. First I called Rick Smalley. I said, hey, Rick, do nanotubes absorb microwaves? And remember, he's the discoverer of C60, and then he was making these single-wall nanotubes. And he says, yeah, they're the best microwave absorbers known, and he hung up. I said, okay. And so I called a student, and I said, here, put these on a watch glass, which is a little dish in a lab. And I said, put it in the microwave oven, tell me what happens. And he came back, he says, it blew up. I said, that's great. These really absorb microwaves. I mean, if someone's going to blow up, it got energy from somewhere, and it got it from the microwaves, and it blew up. And so I called Rick, and I said, hey, these things are great microwave absorbers. The thing blew up. He says, why'd you try that? I said, well, you told me they're great microwave absorbers. I wanted to see how good they are. And it turned out that you get a microwave source. You take it out of the oven, you just put the microwave source in front. These things, you put them in an evacuated tube so they don't blow up, and they just glow white hot. This is white body radiation. This black body radiation gives us white light. And so you see this amazing heat. These would heat to 2,500 degrees in seconds. And they can get much hotter than that. And you can even see the fusing of microwaves. After you heat it up like that, you can see this fusion, the fusion of the nanotubes, where one nanotube did this weld to another nanotube, where the carbons just welded. Isn't this interesting? You could do this. And so we thought of putting this in airplane wings. And what you want to do is you want to change the stiffness at different locations. That's a very hard thing to build in a material standpoint. But you can just apply microwave more here, less here, and then none. And your stiffness is going to change along this. This is how we hear all these different tones. There's this little bar in our ear, and the stiffness, the modulus of this bar changes as you go along. This is how we can hear all these different tones because of this stiffness change. So to have a material where you can get a stiffness change like that at different locations. And then I'll wrap it up with this. So these are shuttle tiles. Shuttle tiles were on the space shuttle, and they were having trouble with these shuttle tiles coming off. They needed some way to be able to apply a new shuttle tile in flight. Some came off on takeoff, but there was a NOAX resin holding it on. That is a ceramic resin. It's a ceramic. And these things are made out of a very lightweight ceramic. And so they use this, what they called a NOAC resin. So they said, I said, you put this on there, but this needs 1800 degrees to cure. On Earth, you put this in an oven and it cures and it sticks. But how do you cure it in space to 1800 degrees? You know what they told me? They said, we put the things on and we hope that it cures upon re-entry. I mean, you're flying in at this enormous rate of speed and you want it to heat up and hope that the thing cures and the shuttle tile sticks? So I called a student and I said, mix some of these nanotubes with the NOx resin and put it in the microwave and see if the thing will cure. Sure enough, it cured because the nanotubes will get up to 2500 degrees. So NASA developed a microwave gun that could be used in space where you put the shuttle tile and then you shoot it with this microwave gun and it cure it and stick the shuttle tile. And I wanted to practice on real shuttle tiles, but they wouldn't give it to me because they said, this is proprietary material. We can't share this with you. So Rice has had a long relationship with NASA for many, many years. And my student found a box of shuttle tiles in one of the labs back before they thought this was proprietary. And so we cut them up so that we'd have a lot of them. You know, you're still dealing on pieces. And they came in, they said, where'd you get the shuttle tiles? I said, don't ask, don't tell. But we came up with this technology. And so you see this astronaut with this microwave gun. Now, actually, that's not a microwave gun. That's a water gun that I photoshopped in. But they wouldn't show me the microwave gun. I never saw it. So they're using our technology. I could never touch them. I never could see the microwave gun. So anyway, I just wanted to get the point across. So you can see, you know, when you can see these nanotubes coming out of the resin if you break it. So we are going to end there. Are there any questions? Okay, remember, you got 1 week for another invention, and hopefully your inventions get more and more sophisticated and make you more and more money. I haven't graded them yet, but I will this weekend. Okay, thank you. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.